Hello everyone and welcome to a new video in which we will be doing stock price prediction using LSTMs. So we will basically try to predict the stock price of a particular stock using LSTM in PyTorch. So let's see how we are going to do, or rather let's see how we are going to approach the problem. So we are going to take, for example, the Netflix stock prices. As you can see over here, this is the head of the table. There is a date column, there is high, low, close and open and close, and then there are volume and adjusted close. Now obviously we are going to do only one of those, that is I'm going to do for close. You can follow the same thing and do for the open, low, high. So I hope you understand how stock prices work. So close is basically at what is the last price of the day. So if we are to print this, the way we have to approach the problem is, let's say we have the close in a particular close prices is in a particular array. So obviously this has right now I'm just showing five of those rows. There are thousands of rows. So let's say they are, for the purpose of demonstration, there are this many rows. Okay, and all of these are like, this is for the first date, second date, third date, fourth date, fifth date, and so on and so forth. This is the closing prices for all the days. What you have to do is you have to initialize or take one variable, that is the sequence length. You have to do that. So I'm going to choose, for the purpose of demonstration, sequence length equal to 3. I'm going to show you how the data is created. So sample 1 is created by taking the first sequence length element. So obviously we'll go to the start, and what is the sequence length? 3. So we'll take the first 3 elements. We will write 251, and what is this is going to be our training data. What is the target for this? The target is the next day data, because at the end of the day, what we want to do, we want to predict the next day's stock price. So you have the history data and you want to predict the next day. So for this 3, this is the next prediction. So can you guess what is going to be the next data? Obviously this thing will move one step to the right, which means now it moved one step to the right. We will take sequence length data, that is 518. We'll write it over here, and then we are going to have the next day. What is the next day? The next day is 6, and this is going to be our target. Similarly, you can go for sample 3, sample 4, sample 5, and finally you can go for the sample n, which is the last part. Over here you can see 11, 9, 7. You can see over 11, 9 and 7, and finally we'll predict 1. So here obviously there are not many, but in the code you're going to see thousands of samples, and sequence length will also be a lot bigger. Now let's see how you're going to approach this problem with an LSTM. So we will take first sample 251. If you remember from here, our first sample was 251. It will be given to the neural network, which in our case is going to be an LSTM. So 2 will be given to the first LSTM. Obviously it will take another size, so same LSTM but in the different time steps. So this is distributed along time. Okay, then the hidden state and cell state will be given to the next LSTM, and the next input is going to be 5. It will be given again, 1 will be given. Now the output of the last LSTM cell, whatever the last time step, will be given to a simple feed forward neural network, and one value will be predicted. So let's say this predicted value, here I have given the correct. It could be, while the training it will be something different. Whatever will be the difference, it will be used to calculate the loss, and then back propagation will come into effect. Okay, so now let's go and implement all of this in code. So here we are with a empty code over here. Now what I'm going to do is I'm going to import the basic libraries. So as you can see, I have imported the basic libraries: NumPy, Pandas, sklearn. We are going to use the minmax scaler for scaling the input, and finally matplotlib for plotting. The first thing that we need to do over here is import the data frame, or rather load the data frame. So I'm going to say pd.read CSV, and the file name that we have, capital C has to be removed and small c, and the file name is netflix.csv. So I'm going to just print the head of that so that you can see that it is the same. Okay, so I'm going to hit there, and so as you can see over here, the same thing that I showed in the slides: date, high, low, open, close, volume and adjust. So we are going to only take the close one. So for that, what you can do is you can go over here and say closed prices, and the way you say you only want close is by specifying the column. Okay, once you are done with that, what you need to do is you have to define the sequence length. So in the slides I showed you 3, but here I'm going to take 15 because we will be using 15 as our sequence length. Now obviously what you need to do over here is to define the min-max scaler. So is for the min max variable, so min max scalar, and here I'm going to just pass I'm going to say scaled price. So I'm going to pass the closed over here and then have the scaled price. So I'm going to say dot fit underscore transform. Okay, and I have to pass here the closed prices. So first I'll convert it to a numpy array if it is already not in that uh, type, and then finally increase its dimension, because this is how it takes. So I'm just adding one dimension at the end, nothing. This is just a simple list. If you also want to see it, I'm going to show it to you. So here you can go and say print closed prices. Okay, so let me go and rerun. So as you can see, it's here, it's all the prices are there, so it's basically one dimensional. Okay, now here what you did is you remove the print, and here what you did here in this place, you basically increase the dimension so that you can fit and transform that. And lastly what you need to do is just squeeze it back. Okay, so that again you just have a list. So if you print the scaled prices, so you can go over here and say scaled prices, and then you save an F5 scaled price. You can see over here there is a simple list. It has again come back to a simple list. So this is what we wanted over here. Now let me define two variables. X is going to be our data and Y is going to be our target. So both of them are just simple empty lists. Okay, now I'm going to create the data. So for I in range, so you basically see how many of the times over here you can go. So how many of these iterations are going to be there? So one iteration is this, then one step it will move to the right, again second step to the right, third step to the right, and so on and so forth. It will move how many times? N number of times. So what will be the n? N will be, it will be length of scaled price minus sequence length. Okay, so this is going to be the number of times that this particular loop will run. Now what I want is x dot append. So I'm going to append the data. So I'm going to say scaled price from where to where? From I to I plus sequence length. Okay, so from ith position you have to take to the I plus sequence length position. So basically you will have I plus or you'll have a sequence length window. Now the target will be what? The target will be again scaled price, but it will be the next value, which is I plus max sequence length. Why? Because when you take I to I plus sequence length, let's say 0 to 5, the fifth element won't be here. Okay, but here the fifth element will be there. So this is how it works. Now you already have these you already have the data, so I'm going to actually show you the data. I'm going to say length of capital X. You can see 4866 is the total number of data. So if you go and see what is x of 0, and let me remove all of this so that it is clear. So you can see 15 values will be there. Okay, so this is what I wanted to show you. Now what I'm going to do is, now I'm going to divide it in the train and test. So I'm going to say train underscore x, which is going to be our training data, from torch dot from numpy. So we will be using this torch dot from numpy. Now what do we want? We want capital X. From where to where? We just want 80% of the data to go to the training part. So I'm going to say int 0.8 into x dot shape of 0. Now ideally what you can do over here is go back a little bit and change x. So x is equals to now numpy dot array. You have changed it again back to a numpy and increased the dimension at the back. So dot dot dot. Okay, you basically have done this. And again y, you have to do the same thing. You have to change it to an array, numpy array, by saying np.array, and then you again have to add a dimension at the last. So once you are able to do these two things, you are able to run this entire query. Okay, now lastly you have to convert it into a float because we want to run backpropagation on this. Then train x will remain the same, but we will change a little bit for train y. So I'm going to say over here y, and instead of x we will have y, and everything else remains the same. Now for test, you have to change this, this will remain the same. However, now you don't want to end at 80%, you want to start at 80%. So you have to take the colon from the left hand side and put it on the right hand side. Now the same thing will be done for the test of y. So I have to change it to test. Instead of x, I'm going to have y, and instead of x, I'm going to have y, and I have to remove the colon from here to here. And the way you verify this is, first let me get some space here, then you go back over here, and then you print train x dot shape and then test x dot shape. Okay, now hit F5. Okay, torch is not defined, so you need to import torch. You can go on the top over here and say torch, import torch, and import torch dot nn as n. Go and hit F5. You can see over here torch.size is 3892. These are the number of training samples, and 974 are the testing sample. Every sample has 15 sequence length, and here also every sample has 15 sequence length. One is used for increasing the dimension because this is how LSTM wants the data to be. Okay, so now you have the train and test data. Now what you can do is, finally you can start building the model. So I'm going to say class model, and I have to inherit from nn.module. Okay, I want to change, or rather not change, I want to define the init function. Here I want two things. I want the input size, and I also want the hidden size, because you need to specify input size and hidden size in an LSTM. Lastly, I have to pass the super and then init, and finally you have to define the LSTM. So the way you define the LSTM is, you say nn.lstm. finally you define the input size, so I have already gotten it from there, so I'll be giving it. Then you define the hidden size, which is hidden size over here. Lastly, what you also need to do is define the batch size, or rather not the batch size, you have to say batch first equal to true, because our batch number was at the first dimension. Okay, so once you are done with that, what you can do is, now finally you define the forward connection layer that I had shown you in the model. That is the, whatever the last output is there, it is passed towards the last layer. So I'm going to say self.fc here, and then finally I'm going to pass instead of self.lstm, I'm going to go here and say nn.linear, and then pass the hidden size, not the hidden state, and then finally we are going to predict one value. Lastly, we are going to have a forward function, so I'm going to say forward, I'm going to say self and then pass the value. After that, we are going to say output comma hidden comma cell equal to self.lstm x. So basically x was whatever the input that we had, we passed it to the LSTM. Whatever we get the output and hidden, what I'm going to do here is I'm going to return the output from the FC. Output of what? So output here will be I'm going to return -1. So I'm going to return from the last LSTM cell in the time step. If you remember from the I can also go and show you. If you remember from here, the last step, the output, it was passed through the single connected layer. So I'll go back to the code and I'll keep it like this. Now what I'm going to do is I'm going to instantiate the model. I'm going to say capital model and then pass the two parameters. What is going to be the input size? Input size is 1. What is going to be the hidden size? Hidden size is going to be, let's for example assume 96. Okay, you can definitely change it. You can also change from output to hidden. So if we don't get a good accuracy, we will change it from output to hidden. Okay, now once the model is defined and instantiated, what we can do is define the optimizer. So we can say optimizer is equals to torch.optim.adam. So we are going to use the Adam optimizer. You can say model.parameters and learning rate is going to be 0.001. Finally, what you're going to have is the loss function. You're going to say loss function is nn.mse loss. MSE mean squared error loss. So basically we are going to predict real numbers, that's why we are going to have MSE loss. Over here now what you can do is you can write the number of epochs. Number of epochs is going to be 100. You can definitely change it. Now finally we are going to write the training loop. So I'm going to say for epoch in range, what is going to be the range? Num of epochs over here then you can go down and finally pass the entire training data to the model at once. Why? Because the training data is too small, so you can pass it to the model itself, the entire training data. Okay, now what you can do is you can find the loss, you can say loss function, and then you can see the difference between output and train underscore y. Okay, now you need to write the backpropagation part, so you'll say optimizer dot zero grad for zeroing all the gradients, you can say loss dot backward for running the actual backpropagation, and finally you can say optimizer dot step, that is it will change the weights in the layers. Okay, so once that is done, you can say if epoch modulus 10 equal to 0 and epoch not equal to 0, which means whenever you run into a epoch that is divisible by 10, so 20 30 40 10 20 30 40 50, but 0 is also divisible by 10, but I don't want at the 0th position, so I have removed the 0. So I'm going to say print. So what we are going to print, we're going to say what is the epoch, and then you're going to say loss, epoch loss, and then finally print the loss. So the loss is loss dot detach. So ideally I would have written CPU, but I don't have GPU, so there is no point of writing CPU over here. Then you detach numpy, and hopefully this should suffice till here. Lastly, what I want to do is I want to evaluate the model finally. So I'm going to say model dot eval. I have to get some space here, and finally what I also need to do is with torch dot no grad. So I don't want to have gradients, which basically means that I'm going to have an inference. So I'm going to say pass model, we are going to pass the test data that we had gotten, so we are going to say test underscore x, and finally what I need is I need to print things out. So the way I'm going to print it out is or rather I have to first change it. So I'm going to say dot inverse transform. So first we changed it to min max scalar, now we want to get back our original thing. So out is going to be let's say output dot squeeze. So we are going to squeeze it. Lastly what I'm going to do is, or let me just call it pred. Okay, pred. Lastly what we're going to have over here is we are going to have the real, which we can say inverse transform, and instead here we can pass test y dot squeeze. So output is the predicted one, as you can see over here, output dot squeeze. So this is predicted, and what is real? Test y is real. Test y is real, so that's why you have the predicted over here and you have real over here. Lastly what I want to do is I want to plot both of these. So I'm going to say plt dot plot, and we are going to pass pred. I'm going to give the color, I'm going to give this as the red color, and I'm also going to give it a label. I'm going to label it as predicted. Okay, lastly I have to go over here, copy this entire thing, go to the next line, plot it, and instead of pred I'm going to say real, instead of red I'm going to say green, and instead of predicted I'm going to say just real. Okay, lastly I want to show everything over here, so I'm going to go over here and say plot dot show open close brackets. So let's hit rerun and see if there are some mistakes in the code. Okay, there is one mistake. Instead of squeeze over here I had to convert it into numpy because this was in the PyTorch format. Okay, so I have to convert this into numpy and this into numpy. Okay, and instead of passing just pred, we have to first squeeze it. So UEZE, and here also we have to do the same thing, we have to squeeze this. Okay, so these were the two things that we had to change. So SQU, and then finally have this over here. So now I'm going to try to hit F5 and rerun. So as you can see over here, we did not quite get the right result. Yes, the pattern is almost same. It has been able to find the pattern, but still we can do a lot better. So one change that I would like to make is you can go over here, and instead of giving the output you can give the hidden. Okay, hidden, and just remove the last part. Okay, so now if I hit rerun, so you can see over here we have a much better fit. As you can see, the lines are almost converging. Definitely you can change a lot more things over here. You can tweak a certain parameters, and you can also see the loss has been decreasing quite really well. So you see the loss has been decreasing. You can change a certain things here and there. You can change the hidden size from 96 to, let's say, 128, or you can even reduce it to have all those things. You can also have over here, let's say dropout, number of dropout, and number of layers also there. So like you can say number of layers. So basically what you can say that you can do a lot of things over here. Okay, so I hope you understood. The video code is in the description, and